Hello and welcome back to Calculus 3. We have 13.3 on double integrals in polar coordinates. Something is misspelled in the title, so let's fix that. There we go. Coordinates. This means that the YouTube has the wrong title too, but such is life. All right. So double integrals in polar coordinates. We have the polar domain. You guys learned that in pre-calculus, then you learned it in Calc 2, chapter 10. The polar coordinates are for 2D, XY. So it's still done on the same XY graph. Polar coordinates are just a different way to reach a point. If you remember, a polar coordinate point is given with r comma theta. So to reach a point, you would first stretch radius r, and then you swing that radius angle theta to reach the point r theta. So it's supposed to graph 3 and pi over 6. The way I would do that is I would first draw the radius. Let me do that red. I'll draw the radius r, which is 3. And then I would go to pi over 6. Now pi over 6 is 30 degrees. So I would swing pi over 6 to reach the point, single point, 3 pi over 6. This is still on XY grid, right? It's still on XY grid, but it's a different way to reach the point. Instead of going in a rectangle, which is why XY is called a rectangular coordinate system, instead of going in a rectangle, when you go 3 units in X and then you go maybe 2 units up, now you are going 3 units R on X, and then you swing that in a circle, right, for the angle that you need. Positive angles go counterclockwise, negative angles go clockwise, and positive radius you draw on positive x-axis, negative radius you draw on the negative x-axis. So negative 3 pi over 6 would be actually here somewhere, because you draw negative red, negative 3, and then you go counterclockwise pi over 6, so you would go down, right? If it was negative pi over 6, you would go up, because that would be clockwise. These skills are there in chapter 10. If you need to brush up on this, please go look up lectures on YouTube on polar coordinates, right? They're there. 10.3 or 10.2, whatever, is the basic, just pre-calculus, and the second lecture is calculus, how to integrate areas there. And guess what we need? We need that, exactly that, right? Because we're going to have area on the base times the height to give you the volume. You know, Calc 3 is volume. So that's a brief introduction to polar coordinates, and now we are going to take a look at the formula that we need to compute volume for objects whose domain would be suitable for polar coordinates. So circles, flowers, cardioids, and all of those things that you guys learned in Calc 2 in polar coordinates sections now are going to be our domains. So now your stencil for cookies can be a flower. Your stencil for cookies can be a cardioid. So, you know, to make a, Valentine cookies, you a shape of a heart, right? So we have that given in polar coordinates as a cardioid, right? So you can create cookies in various shapes. They're no longer boxy, right? Our 13.1, it was a rectangular domain. All of your cookies had the rectangular shape, and they were boring, right? Then we add for different kind of shapes which are weird shapes for cookies. You generally don't have, I mean, you can make a cookie in a shape of a football, flattened, right? That would be two parabolas, right? Actually, I should have this baking assignment. Yeah, you get a mix for like $2-3, and then you shape them in shapes, and then you just compute the volume of each of the cookies, and you can compute the caloric values and all of that stuff because it's given in a box. That's a good project problem. Take pictures of baking stuff, right? And see, you can make a project out of this easy.
And then you get cookies at the end.
That's going to be a lot of cookies. The final exam, everyone is bringing a batch. Right, we can have a bake sale for Horak. But the thing is, it's so 13.1 boring rectangular cookies. 13.2, the best you can probably do is the football shape, but flattened, right? Cookies. And now in this 13.3, they can be in shape of a flower or shape of a heart, so something that actually, you might see cookies be shaped. And circles, obviously. The chocolate chip, right? That's what we're doing right now. You do not want to do chocolate chip with other coordinates. So let's talk about some shapes. So where do I begin? First, let's talk about polar coordinates a little bit more. I need to make sure that you know that circle, which is x squared plus y squared equals to r squared, in rectangular coordinates is given as r equals a number, so r equals constant in polar coordinates. And you can immediately see where all of these horrors in calculation go away, because your previous problem we did in 13.2, x squared plus y squared equals to 9 for rectangular coordinates transfers into r equals 9 in polar, eliminating all of the trig subs and all of the u subs and all of the horror of calculations that you have there, because polar coordinates are built for circles and those rounded domains, where xy is looking for edgy stuff like triangles and squares and rectangles and things like that. So now I would like to take a look at the problem we discussed earlier. I have some elliptical paraboloid over here, which is 9, and then this shape over here, x squared plus y squared equals z, right? So I have these two, and I would like to know the volume. Well, what would be the integral that would compute this? We have to actually have a formula first that we use. So the volume is going to be given by the double integral of the function given in r theta, and then we have this string that is the same string you guys have in polar coordinates, which is r dr d theta. So this r over here is, in some cases grade killer, so make sure that you have this as a unit. This is a unit, right? A block. Just like you have dx dy, now you have r dr d theta. Why? Well, first off, check the dimensions of this. Function is a dimension. We use that as a height. Radius, that's a length, so that's a dimension. dr, change in length, also a dimension. d theta, not a dimension, right? It's not a dimension. What's theta? Theta is an angle, right? And what's an angle? An angle is the ratio, right, of sides, or the arc length, right? So you have that the arc length is equal to radius times theta. So theta is the arc length, which is in inches, let's say, divided by the radius, which is also in inches. So what are the units for theta? There's no units for theta. It's not length. So therefore, d theta does not provide you with a dimension. And that's good, because I already have 3 dimensions. If this was a dimension, it would be the 4th one, and that would be bad, because I'm looking for a volume, right? So dimensionally, this equation makes sense. And we have this as the formula that we have to compute. So what is a good thing about this? Oh, I forgot to put the limits, sorry. We have alpha to beta. Those are the angles for theta. And then I have A to B numbers for my radius. We are going to modify this, and we are going to put functions instead of A, B eventually. Not yet. We are going to put functions there. So what am I working with over here? Well, first off, I'm going to point to this alpha beta thing and say that, you know, this is your domain. And note that if I have a circle in my domain, I can get half of that shape up there, like this, if I use alpha equals 0 and beta equals pi. Does that make sense? I can create a wedge, like a pizza slice cut in quarter, if I go and I take 0 to pi over 4. Now, what is that going to do to the shape? That actually is going to cut the wedge out of the shape and just find the volume of that wedge. Right? Do you know how when you have the watermelon, you can just cut out one slice long way and take it out, and then you have the rest of the watermelon with the wedge piece missing lengthwise, right? How much did you cut? Well, you cut whatever it's circular, right, on the one dimension of the watermelon. So you cut certain theta out. What did you cut? Pi over 4? That's an eighth of the watermelon. Pi over 16, right? How much did you cut out? So if you cut the watermelon in half, that's 0 to pi, because the entire watermelon is 2 pi going around. So the alpha and beta are going to be domain. So if I only shade half of the circle, right, it's going to be 0 to pi. Now we are using, in our case, 0 to 2 pi, because it is full circle for our picture. So I'm just going to get rid of this stuff. I was just explaining a little bit. And then you have A and B, that's a radius, R, which in our case is 0 to 3, right, because you are taking all of it. 0, arrow 3, 0, 2, 3. All right, let's set up this integral and solve it. I promised like a one-line solution, so see if I can live up to that. First, we set this up. I see that the volume is going to be double integral, and now I need functions in terms of r and theta. Well, I know that x squared plus y squared is just equal to r squared. So what I have is 9 minus r squared, r, dr, d theta. What am I doing here? I'm doing top minus the bottom. That always stays the same. I mean, there is nothing new there to learn. I have the top of the shape minus bottom of the shape, except now top is just a flat plane, so 9, and then the bottom is and then I have the limits. I want the full circle, 0 to 2 pi. That's the full circle going around. And then I have the limits 0 to 3 for the radius. That's dr, radius, 0 to 3. So what are you integrating? You're integrating 9r minus r cubed. And you just have basic numbers to plug in. Can we accomplish this in one line? I hope we can. So the integral 0 to 2 pi, the inner integral is 9/2 r minus r to the 4 over 4. I hope you're remembering these numbers as I was mumbling, trying to do this mentally. So we have 27 over...
Where's the over 2 come from? Not over 2 How did that?
Well, when I am integrating 9r, right?
Oh, okay.
Because r has to distribute. So this becomes 9r, and this becomes r cubed.
Okay, never mind.
So integral of r is r squared over 2. All right, so that's that, minus 81 over 4. And guys, this is a constant, right? With the integral 0 to 2 pi d theta.
9r squared over 2.
Oh, 9r squared. Yes. So that's bringing another... Oh, this is even better. This is 81. Thank you. That's 81. So the whole thing is just 81 over 4 integral d theta. So the answer is 81 pi over 2. Boom, done. That's your volume. Welcome to polar coordinates when you have circle as the base, right? So if you have circle as the base, the polar coordinates are the way to go. We have 3 trig subs here to do. Now, if you go and you spend an hour, right, in the previous problem and do those 3 trig subs, eventually, right, 81 pi over 2, over 4, over 2. All right. So let's take a look at more of these examples. The picture that they have, the example they did in the book is just upside down. They do have 81 over 2 as the answer. Please note that if I am to stand this object up, it's something that you pick up. It doesn't matter which way you turn it, it has to have the same volume, right? It's not that you have your bottle of water and you flip it upside down and now it's twice the volume or something. It's going to be the same no matter which way you put that. No matter which way you turn that bottle, it's always going to have the same, whatever, 16 ounces. Whatever. Yes?
So, I guess I'm having trouble picturing the other side. Basically, what I'm asking is, so if you have like integral, so someone goes integral from A to B and then integral from C to D, times whatever, is the domain A to D or is it A to B and D?
The whole thing, both integrals are okay. And so you're looking for volume, right? The volume is going to be the area in the base, and that's given by dx dy integrals, right? The area of the base. And then the height is given by functions which are the shapes that shape your object. So you have area, which is dx dy, which are both on the floor, times the height of the function to give you third dimension to get the volume. Let's take a look at more examples here. This is an amazing example. for you mechanical engineers and other people that are making tools and stuff. Look at that thing. He has a hole inside. He has very sharp edges. The top, whew, that thing is sharp. All right. So this is some kind of cutting tool. I don't know what it is. It's just some kind of cutting tool, probably that makes holes in pipe, and then you have there's a tube in here, maybe to, you know, put the heel or whatever out. I don't know. So what's the volume of this? You're going to say, why would I need that? Because you need to make 100,000 pieces, 1,000,000 pieces. How much raw material? You can't just go and say, pick me the you know, 2 trucks of, right? It's not how you order stuff, okay? Your job as engineer, if you're designing this tool, is to give them also how much raw material they have to order, right? And that you don't estimate that stuff because it's expensive, all right? And you're an engineer in a company, so this is your job, to figure out the volume of this thing. And what do you have? You have a circular domain with a hole inside. So now, right, we have to deal with that. Then you have the top function, which is the wavy stuff that we see here, given by xy plus 10. And then the flat bottom stands on the floor, so -0. At least we don't have to worry about, you know, that. So we're just integrating this. But now I need polar coordinates. That means that I have to transform this xy plus 10 into polar coordinates. Done here. Plug in. You have this. Because, yeah, this is a very nice function to integrate. But look at your domain. You know? This is going to scream like 16 trig subs, all right, by the time you get there. So, you know, you pick your battles. So now we have this shape. I'm just trying to draw this so you're not missing out on anything. We have some kind of right over here.
Screen.
Yep. I'm just trying to draw this, so you might want to look at that and try to draw, not at what I'm drawing. Eventually I will switch. So now we have this happening, and then it's 3D and stuff, but I'll just leave it there. We have a hole inside. That hole will permeate through the object. This is where your computer graphics and your AutoCAD and stuff kicks in. And I have my Z-axis, my X-axis, my Y. I know. On purpose. As I said, look at the source and try to draw it. Don't look at what I'm trying to draw, because it's not gonna be as shiny. Now I have my domain, which are those 2 circles, and the radii 2 and 4. So I need that, and I need the surface over here, z equals xy plus 10. All right, so now I can switch, and we can go and solve this problem, discuss all of it. So this is some kind of cutting tool or whatever it is, right? It has a hole inside and has these sharp edges up there. The formula for the entire shape is given. That includes this cut and everything. So I'm deciding to use polar coordinates because I have circle in the domain. Right, so you should always opt out for polar coordinates if you have a circle. This is called an annulus, the 2 concentric circles, right? Where, like a washer, right? That's what. But this is a 2D. There's no thickness to it, so that's what it is. And what do we have? Well, first off, if I am to use my formula, which is double integral f of r theta and then r dr d theta, immediately I observe that I need my function to be given in terms of r and theta. I can't put x and y and integrate in respect to r and theta. So I have to do that transformation first. What are the 4 formulas for conversion? One formula, so I'll write those in red. So these are the formulas that are converting polar to rectangular, rectangular to polar. Again, all of this stuff, 10.2. If you don't know these things, y equals r sine theta, x equals r cosine theta, r equal square root of x plus y, x squared plus y squared, and theta equals inverse tangent no coughing over y over x. There we go. So these are the 4 equations that are converting between the realm of rectangular and polar. So now, clearly, I'm going to plug these functions in and go from there. So z is equal to r cosine theta times r sine theta plus 10. Z is equal to r squared sine theta cosine theta plus 10. Now we're going to use one of the trig identities that says that sine 2 theta is 2 sine theta cosine theta. Please look at the right-hand side. You have sine, cosine. So just move 2 to the left, becomes 1/2, right? So z equals 1/2 r squared sine 2 theta. And conversion is done. Yes, plus 10. So right there. Please pay attention. See? Right there. It says plus 10. So what we did here is we converted the formula from xy. Now, is this better? No, this is much worse, right? Much worse. We had basic x and a y. But when you consider the way you integrate, you actually see it's not a problem, right? Because you will be multiplying this by r, and then when you're integrating r, dr, that's just like integrating x cubed, right? And then when you're integrating sine, you're not bothered by x squared at all. So it's not that bad, right? It's not that bad. Time for us to put this in the integral. Double integral of 1/2 r squared sine 2 theta plus 10, all in parentheses, because we have r, dr d theta, right? We have this plus 10 that it's, you know, just there. So we need those parentheses. Time to figure out the limits. See, do I want the entire tool, or I want the half of the tool, or a quarter of the tool, or, right? I want the entire tool. That's 0 to 2 pi, right? I want the full 0 to 2 pi, the full revolution, right? I can get half of the tool if I throw away half. Make sense? So 0 to 2 pi is the entire tool. And then what's the radius? Well, the question is, where is the material? Between two circles, so 2 to 4. Right? So between 2 to 4, right here, is where the metal is. This is empty, so I'm not using it in mine. Right? If there was no hole, what would be my limits? No hole. 0 to 4, because everything is made out of metal. Right? But there is a hole inside, so I don't need that. Right? So I'm not going to use that in my volume. Yes.
So the limits with the theta, it's always going to be 0 to 2 pi if it's a circle, no matter what, right?
If it's a full circle, yes.
You can't use this with anything else besides a circle. Correct.
No, the flowers, if I want one petal of a flower, depending on how many petals I have, it's going to be, 0 to pi over 8, or 0 to pi over 2, or, So, depends on what you have. Each petal on a 4 petal rose is going to be 0 to pi over 2. Because you have 0 to 2 pi to draw the entire thing, right? If you have 4 petals, then 2 pi divided by 4 is pi over 2, and that is how much will take to draw one. So 0 to pi over 2 is going to draw a single petal. So you will have to be careful. No, those problems are coming up, so we're not going to rush into it. It's just that, right now I want the full thing, so 0 to 2 pi. Every time you want the full thing, 0 to 2 pi, because that's what it takes for trig sine and cosine functions to make a full revolution and draw entirety of what they have to offer, right? And then you can just get smaller than that, right? So now integrating this, guys, should be a joke. Please distribute that r, make it r cubed and 10r, and then integrate in respect to r first. Get your polynomials, plug in 2 and 4, and then integrate theta, plug in 0 and 2 pi. right? I'm just gonna fly through this, and then we do the rest of the stuff. This is gonna be r cubed, so r to the 4/8. Copy sine 2 theta, it's a constant, plus 10r from 2 to 4. We still have d theta to worry about. 0 to 2 pi. Plug in 4, that's r to the 4, that's 256. Oh, wait, I can kill 1 r. So 64 and then 32. Is that 32? That's true, that's 5r squared. Yep. So 32 sine 2 theta plus 20r plus 2080, right? Minus, plug in 2, that's 16, that's gonna be 2 sine 2 theta minus 20 d theta. 0 to 2 pi. 32 minus 2, that's 30 sine 2 theta plus 60. I hope that's good. And then we have integral of sine 2 theta, that's a negative cosine, so negative 15 cosine 2 theta plus 60 theta. You have this 2 that through the u sub will come out as a half, which cuts 30 and 15, and then integral of sine is negative cosine from 0 to 2 pi. And we have plug in 2 pi, cosine of 2 pi is 1, so we have negative 15 plus 120 pi minus, and minus from there makes a plus. When I plug in 0, that's another 15, so that cancels. And then minus 0, so who cares about that? So 120 pi, which is, as you can see over here on in the book, 120 pi. About. Woohoo! Yes. So this is our integration. You do the inner integral dr first, and then you do the outer integral, which is d theta.
Shouldn't it be the 2 sine, because 2 sine pi theta cos theta, because it is the sine 2 theta? It's in the here. Sine 2 theta.
Yeah, sine 2 theta. So when you integrate it, it becomes negative cosine 2 theta over 2.
So why is it negative 2 then?
When you integrate, right?
Yeah.
This 2 will come out as a 1/2 because of the u sub.
Okay.
So half of 30 is 15. Integral of sine is negative cosine. Cosine of 2 pi, 4 pi, 6 pi, 8 pi, right, is always 1. Cosine also of 0 is also 1. So you have there minus 15 and then plus 15. So those go away, and you know, altogether we have this. Polar coordinates are fun. Let's see if we can find. Ah, there we are. The doom. All right, so now. Oh, I didn't see.
Okay, I got it.
Got it? Good. So now let's take a look at the second part. Obviously, I'll write all of these down, but I just want to show quickly what's given to you in the book. Here's the new set that we're working on, and please note that the inner integrals now are functions. Why are they functions? Because I'm going to worry about two polar regions intersecting in a domain, right? Well, isn't that just f minus g? Yeah, it is, right? It's the area between the two. Now, what I call a representative pizza slice, because no longer representative rectangle, right? Your representative d theta, right? That's going to be some pizza slice opening, right? So a representative pizza slice is centered at the origin, goes outward, so it's always outer minus the inner. Outer R function minus the inner R function. And then you build your shape Z on top of that. So what's in the domain now? There's like this crescent moon over here. We all see crescent moon shaded. That crescent moon is your domain. And then the shape builds upward on top of that with the straight walls up, right? And then whatever wavy top you have. That's given by the Z equals. So your domain now, this crescent moon over here, is going to be outer R function minus the inner R function. Well, that's your lower limit, that's your upper limit. And they are given as R's. And look, R as the h of theta and R as the g of theta, because that's the R, the inner integral. So it all fits together. We're going to write this down and then take a look at examples where domains are no longer just basic circles. Now we're going to intersect a flower with the cardioid. Hopefully not, but we can. And so on. So what happens next? So now we're moving away from the domain that is circular into the domain where we are intersecting two functions in a polar domain to create a shape for the domain and then build the object on top of it. So the example given in a textbook are two circles like this, and then they shaded this crescent moon over here as the domain they want. And they say, you know, we need to look at that part. Now, what I do is I draw the representative d theta, which is this. I call this representative pizza slice. D theta. It's like you go to kids' party, you know, and they give you that shredded pizza, you know, the very thin slices. That's exactly what it is. And this representative pizza slice is going to swipe from whatever the angle on the bottom is to the intersection whatever the angle on the top is, and that's your alpha and beta limits. Alpha and beta limits are given by those values. You get them when you intersect two functions. Now note that your representative pizza slice is always stuck between the outer function and the inner function, which are the ones that are creating the crescent moon in this case. So what am I going to have? Let me give you also another example. I'm going to draw a flower, 4 petals, and then draw a circle inside. And then just graph, you know, one of these. It's the same thing. You will have your alpha and beta limits, you have your outer, and you have your inner. Outer R, R1, inner R, R2. Those are your limits. Or, no, the other way around, better if I put inner R1 and this one R2, because then it's going to be R1 to R2. Better. All right. So when you're looking at this, you can see that now the volume can be written as the double integral of, you still have your function R theta, R d theta, that's the That's the block that you can't separate and change. And now, for theta, we have our alpha and beta. Usually now these are not 0 to 2 pi, because is, you know, intersection between these is going to interrupt that. And you get them by, I'll write that down as well, solving the equations. This is what's important. The lower limit R1 is going to be some function g of theta, and the upper limit R2 is some function h of theta. So this is our new formula that we need to use to deal with more complicated polar cases. So alpha, beta, get them by solving intersection equation. H of theta, outer function, is the end of d theta. G of theta, inner function, which, as you can see in both of the pictures, this g of theta was mid. I did not draw a representative pizza slice here, so there we go. So this is your representative pizza slice. You see that all the way at the out where it touches, that's always going to be your upper limit, and somewhere in the middle, well, the middle, somewhere within, is the other one. If you're able to draw these things, these problems will be a joke. If you are not able to draw these things and draw the representative pizza slice and see which way, because guys, representative pizza slice is the one that takes care of everything. I can't do this on over there, but if I draw a representative pizza slice which stretches from the origin through the inner function to the outer function, there has to be a point where they start, and that's your alpha. And then it swipes this way, all angles, all the way to beta. You find alpha and beta when you set those two functions equal to each other, because that's where they intersect. And as you have this representative pizza slice, outer minus inner, because this is where it's pinned, so there is the back end of your pizza slice, and back end of the pizza slice is always riding the outer function. That's your upper limit. So that leaves, by process of elimination, the other function with the lower limit. It's a very structured, but you have to sit there and stare at this and practice this to get. I mean, no one is born knowing these things. It's just, you know, the amount of time and effort that you want to invest to actually do that. And if you want to do it right, representative pizza slice is the way to do it. You can't do it the other way, because there's nothing else you can do. It's the only thing that stretches from 0 to where it goes. Its length is r, and its width is yeah, right? So you think about it. You can have a small pie for pizza, and you can have a large pie for pizza, right? What's the difference? R is the difference, right? Because they're both 2 pi. Whole pie is always 2 pi in angle. So the difference between a full slice, which is 1/8, and a kid slice, which is 1/16, is the delta theta. How wide, right? How thick the slice is. That's d theta. But how long the slice is r. So the length of this representative pizza slice is both of these. Its width is d theta, and its length is dr. Right? That's what. So that's why representative pizza slice is so important. And it's the only thing that moves here, because it moves from one alpha, two other beta. Same here. Starts here and it swipes all of these values and then ends up there. You see that the length is adjusting, right? As it goes through from 0 to thick to back to 0. That's your dr. And then the d theta is swiping from 0 to being thick to being 0 again as it swipes. It always swipes counterclockwise because that's your positive angles. So what do I have? The example of two intersecting circles. And I am going to these graphs are not the best, but I have my alpha, beta, and the shade over here, what I'm looking for. The equation on the inner one is r equals to 2. Circle centered at the origin is always r equals constant. You must know that from Calc 2 and pre-Calc 2. Circle centered at the origin is r equals 2. Circle that is shifted, whose center is at 2, right? It has a 4 cosine theta equation. Now you gotta sit down and learn which equation is which, right? Whether it's cardioid and it's flower and all that kind of stuff. And then when they shift, how they change. That all depends on how much knowledge you have from chapter 10. Now, I'm going to draw my representative pizza slice because that's what helps me set up the integral. If you have any other way, I am willing to learn it. I don't know of other way to do this. So remember what we said. R, dr, d theta is the string that I am using to calculate. Oh, hold on. Do we have a shape over here? They're not giving us a function on top, so we're just gonna keep f. This is only practicing the domain. So technically this is just a Calc 2 problem written as a double integral. It's fine. So I need to find alpha and beta. To find alpha and beta, set r's equal. So that means r's, what r's? R equal to 2 and r equal to 4 cosine theta. So when you set these r's equals to each other, you get 2 equals 4 cosine theta. Cosine theta is 1/2, and if you draw cosine graph, which goes on forever, and you put a half there, you see that there are goes this way as well. You see this value and this value as answers, and it's exactly, if this is a 0 here, right? This is 0. No. So that's where the 0 degrees is on the x-axis. So you see that you have negative angle, negative theta this way, and positive theta that way. So that's exactly what we see on the cosine graph. If you draw cosine right this way, and you do the half, you have the negative side and the positive side around this 0 angle. And half, that's pi over 3, right? So theta equals positive and negative pi over 3, if you consider the graph. So I have that the volume is going to be negative pi over 3 to positive pi over 3. We have F r theta r d theta. And limits for r. So the inner r is 2 and the outer r is 4 cosine theta. And that's it. Can't compute because I don't have the function. But that's the answer. Need this to go on. And that's not given, right? So we have to stop. The whole exercise was exercise for you to learn how to deal with the domain. And in this case, we had the crescent moon, right? Which was between negative pi over 3 to pi over 3 on those rays. And then the stuff in between was from the inner circle, which is 2, to the outer circle, which is 4 cosine theta. Then you get some shape on top, z equals, convert that into r theta, plug it here, and the rest is, you know, good luck with integration. You get to plug in 4 cosine theta. Hopefully that works itself out nicely with the rest of the things, and you don't have to do any, you know, too crazy trig integrals, which is Calc 2 again, 7.3, right? Yay. Yes?
Can you do the x is equal r cosine theta and resolve the x value instead of having 4 cosine theta?
But your whole integral is in terms of r and theta. And let me just tell you, you saw what happened when we just had the basic circle in a domain.
Yeah.
Remember the last problem?
Yeah.
Now you have a crescent moon in a domain. Can you just imagine how much worse this would be on top of that 3 integration by trig sub? Right? Exponentially. Can it be done? It's nothing that, you know, about a week of calculations can't do, but this problem is the same. I already had the picture for this. Really no need to do it. I added 4 petals for the flower. They had 2, same thing. It's the same crescent moon, right? Outer function, inner function. All I need to do is to draw my representative pizza slice. They put this green arrow. I hate it. It's a representative pizza slice. That's what it is. Which swipes from here. They have a nice red arrow showing, right, and a black arrow here showing that representative pizza slice starts on the bottom and swipes up, right? So my representative pizza slice goes that way. You find your alpha and beta limits when you set 2 equations equal to each other, and then you find your outer equation minus inner equation. You have to do that by looking into, right, the thing. It's always the one that is further away from origin is the top, and the one that is closer to the origin is the bottom. That's always the case as you're setting these up. Obviously, the whole problem is solved in the book, and look what they're doing. They did not give you the shape on top, so they're looking for area. This is a Calc2 problem done with the double integrals in Calc3. So all of those problems that were actually, like we ended Calc2 with saying, okay, this is, you know, these are the integrals between two. Well, that was the last section in Calc2. Chapter 10 with integration in polar coordinates. And these were the worst problems, right? This is the same problem. Please note that when you integrate this, you get r squared over 2. Remember that the formula was 1/2 function squared. What's the function? F of theta is r, right? R squared. It's the same formula. If I integrate out r, and I just have a top function minus the bottom function inside, each one is squared, and 1/2 in front. So it's the same formula. So we should go, oh, the average one, they give you, again, the average is just the same thing. You have the area. So average formula, you have to plug in, well, this is applied to the problem, but you just plug in the values and you have it. Ooh. Does that sound familiar? Like something you might want to look into? Or no? Would you care about this at all?
Yeah, probably.
Well, look, why?
Oh,
Boiling of an egg.
the boiled.
It's the boiled egg problem for your project. Right? What are you going to do? You're going to trace this thing on a square grid. You figure out what these functions are, and then you can unleash your polar coordinates double integrals on it, right? See that? That's your page 991 in the textbook. You can practice these problems first, and then you can actually, you know, boil the egg and practice this on the real thing and come up with a project. So you can work with these. I want to see what else do we have. Look at these things. These kind of things are actually calculated, guys. This is applied stuff in cancer research. They also have diffusion models that they are computing with differential equations and things like that, because what is cancer? It's uncontrollable growth of cells. Right? It's a mutation, genetic mutation that happens with some people. Now, it was always happening, right? Since the dawn of time. It's just now there's so many people that we see it all the time, right? So everyone's affected in some way. This is not something that just started, 10 years ago. People were always dying of cancer. It's just because mutation is always there. It's just a product of evolution. We try to fight it. We try to learn how to deal with it. And what do you do with it? You cut it out, right? The problem is that if you didn't cut out enough, right, and you try to cut the least amount that you can because it's a person, the problem is if any of the mutated stuff stays, it grows back, right? Because that's what it does. So mathematical models like these, which are the tumor growth and cancer growth, in some cases, are modeled by mathematical equations. And then you add the diffusion models, because what they do is when they have this round shape like this in 3D, they draw down. I went to a few at NGIT, a few seminars that they had talking about these things. And then they have a little ring at the end, like a little ripple right there, which is around, and then it smooths out. So you actually have to make sure you include that ring as well. So those surgeries are never simple, never easy. It's all blood in a way, you can see it, but some calculation computer models there, which are guiding doctors of how much they actually have to cut out in order to get this out. And then obviously, for some people it's successful, for some people it comes back if it was not cut out enough. Now in some cases, when they say inoperable, Why is inoperable? Well, if you are cutting so much that you are actually going to cut a significant part of the organ that is affected, that organ will no longer work, right? So what is the way that we're doing working things right now? Stem cell research for 3D printing. One of the most important things that we have, because if you can 3D print a new liver, who cares about cancer for the liver, right? Or anything like that, because you can always replace that organ, just like a, you change the alternator or a battery in the car. You can change any of the organs as long as you can, cut out little piece from here, wash it out to the stem cells, and then 3D print the organ that you need. Could it be eye? Could it be, right? This is your stem cells. Rejection rate, 0. Now, technology is not there yet, even though 3D printing of organs has been around for like 10 years. The thing is that these organs don't live long enough, like a week or so. But again, first iterations of any technology that we have are going to be bad, and then they improve. So calculating these volumes and things in the current state of our medical research is important, right? And that's why there's so many jobs in those fields, and Cal3 becomes important, right? And even though some medical schools are requiring Calculus 3 for doctors, so they can understand these types of shapes. So if you are a pre-med, I mean, most of you over here, all of you are engineers, but generally for pre-med they say Calc1, right? But then when they actually start medical school, they get hit by Calc3, when they're there to understand, these kinds of things. And then even, differential equations, partial differential equations would be helpful, but again, that's mostly for engineers. There is some use, and you will always have people on top of the field that would be interested in learning and try to apply it to the field to make the whole thing better. So I hope as you're looking at these equations now that you're seeing x squared plus y squared. The whole thing is replaced by r squared, right? So that makes these equations not a problem, right? You also see e to the negative x squared. We know we can't integrate that, right? But if you change this into negative r squared, do we make it better? We cannot integrate negative e to the negative x squared. Now if we change it, and instead of doing the xy coordinates, we do the polar coordinates, why is e to the negative r squared better? It is. I'm asking why, not if it is. I'm asking why it is better.
If you put a cosine and a sine.
Nope. What goes in a box for polar coordinates? Aha, yeah, exactly. Now you got it, right? You see this R, which is a part of the string that you must put every time? Isn't that R you need for the basic U sub? Exactly. So when this over here is e to the negative r squared, you have the R for basic U sub, and the problem is a joke. Try to do this problem in whatever Cartesian coordinates, you can't do it at all. You can't, because you can't integrate unless you reach your Calc 2 and you pull out power series, and then everything magically works, right? Power series can deal with it because power series would take this, turn it into a polynomial, and then you can do it, right? But come on, polar coordinates, we love this R because it allows us to deal with a lot of these cases. So let's take a look at the homework exercise. Let's do 29 because we can. And we have z given as e to the negative x squared plus y squared in parentheses. Everything divided by 8, and then minus e to the negative 2.
Swap those.
Yes, free of charge. So now this is going to be this blob like this. sitting on the xy plane, and the volume of this is double integral e to the negative r squared over 8 minus e to the negative 2, everything times r dr d theta. I want the full circle, 0 to 2 pi, and what are my limits for r? Three. Just put in 3. That's it. Good enough. I said limits, so plural. At least give me 2 numbers. Clearly, it's 0 on the bottom, right? Because it starts here, and there's going to be some circle in the domain. So domain is circular, like this. R starts at 0. No holes in the whole thing. So it's just a basic number, 0 to a number. How do I find that number? That's my question. We have a function z equals e to the negative r squared over 8 minus e to the negative 2. So this is one of the basic skills you have to figure out where the radius ends. What happens to the shape Z? It's going down. And it hits XY plane, right? And that's where the object is the fattest, right? So that would be where the R, Z equals 0. Happens on the floor, right? The object is the fattest as it hit the floor. So this circle in domain, the black line, the outline of a circle, the circumference, is hitting the floor when Z is equal to 0. So when you solve Z equals to 0, that eliminates Z. The only variable over there is R, which is going to be the number you're looking for your upper limit. So let's do this in blue, let's say. Now you're looking at this equation and you're freaking out. It's extremely simple. 0 equals e to the negative r squared over 8 minus e to the negative 2. I mean, you should be able to just look at this and know it's 4 right away. Why is that so? You move e to the other side, so you have e to the minus 2 is equal to e to the negative r squared over 8. And now, look, don't you agree that if e is equal to e and negative sign is equal to negative sign, then r squared over 8 must be 2? So r is 4. Just by looking at the whole thing. R is positive negative 4, but lengths are never negative, so we throw that one away. So you simply equal the exponents because bases are the same. The negative signs on both sides, they drop. And you just have r squared over 8. Move 8 to the other side becomes 16. 4 squared is 16. So the top limit is 4. And now we just need to do a little bit of Calc1 U sub for the first one. The second one is a constant. That's going to go quick. And there you go. What do we have? 8 minutes? Let's make it happen. integral, double integral, 0 to 2 pi, 0 to 4. And now I have over here in parentheses r e to the negative r squared over 8 minus r over e squared dr d theta. So all I did is I just multiplied r inside. That's all I did. So now I have to do a Calc1 problem. Let's do that in orange. So I am working on the orange part over here, which is the integral 0 to 4 of r e to the negative r squared over 8 dr. I'm just going to solve that piece. That's Calc1, u sub. So u equals negative r squared over 8. Du is equal to negative r over 4 dr. So I need negative r over 4. So when I add negative r over 4, then I need to put negative 4 in front. So now my problem becomes negative 4 integral. This becomes e to the u du. And my limits are 0. And then when I plug in 4, that's negative 2. Right? When I plug in 4, it's a 16 over 8 is 2, so negative 2. Good. And now I have a negative number on top. I need to swap that, so it becomes 4 from negative 2 to 0, e to the u du. And that is 4 e to the u computed from negative 2 to 0. When you plug in upper, you have to plug in 0 because it's 1, right? E to the 0 is 1. So it becomes 4, and in parentheses I have 1 minus e to the negative 2. So the total is 4 minus 4 over e squared. So that's the total for the first integral. We had to do some Calc1 there. Not bad. Equal to, I have 0 to 2 pi. And the first integral worked out to be 4 minus 4 over e squared. And now I have minus, I have to do the second integral. That's going to be r squared over 2e squared computed from 0 to 4. And that's just for this part. And I still have d theta to deal with. So 0 to 2 pi, open parenthesis, 4 minus 4 over e squared. And then minus 16 is 8 over e squared. And when I plug in 0 for r squared, that's gone. And now this is negative 12 over e squared, but the whole thing is a constant. So I'm just going to push that in front of the integral. That's 4 minus 12 over e squared. And now I have integral 0 to 2 pi d theta, and that's just 2 pi. So this is 4 minus 12 over e squared, all of that times 2 pi. I can factor out 4, so make this into 8 pi 1 minus 2 over e squared. That's the exact value, I hope. So e squared is about 10, that's a fifth, that's 2/5 of 0.8, so about 6.5 times, about 20. The whole thing. Polar coordinates. What's next? Next lecture, next week, is devoted to triple integrals, because we are done with doubles, right? We have double integral on rectangular, double integral on general regions, and then double integral on polar. All of those are going to have upgrades now into triple integral. And the polar upgrades, one of them is cylindrical, not going to be a problem. The other one, spherical, a problem. All right, so you'll have to pay attention there. Triple integrals on the rectangular coordinates, so dx, dy, dz, are going to be a straight up upgrade where you just have one of those orders. Changing order of integration for that is going to be much worse than what we had the previous time. And I'll have to focus more on changing order of integration for double integrals, and then triple integrals will be bringing in some trouble there. After we do the three types, so that's two sections, three types of triple integrals, so rectangular, cylindrical, and spherical. Then we have applied sectional figure out center of mass. That's the electrical engineers, mechanical engineers over here, to find the center of mass for a car or the airplane or something. That's also, if you're into martial arts, is going to be useful. And the last section is 13.7, which is going to be the section on changing the, like they use sub, but this is a substitution for double and triple integrals. And those are going to be the highlights of the of our calculations. One of those sections when you go about an hour, warm up first, and then you do a problem. So that will be chapter 13, the entire chapter on integration. Then we have 14, and that's the end of the course. So I'll see you all next week. Please look at the project, look at the directions, and I'm going to upload notes and homework now. So please do that as well. And see you all on Wednesday.